Welcome to the Problems Channel Season 2, Episode 51, the episode which I titled A Cube versus a Cylinder, because in this episode we will solve a physics problem that resolves the question of which one of these comparably sized solids is easier or harder to tip over. But before we do that, as a traditional and friendly reminder, if you are joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material presented on this channel is to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions in that episode. If you have any questions, then by all means do ask these questions. When I have time, when I get around to it, I will definitely answer all your questions. And in that episode, we describe and motivate everything that we do on this channel. In the physics problem S2P1, our first physics problem of the second season, we're asked to answer the following question. What is easier to tip over, a uniformly dense cube with the side length of A, shown here in red, or a right circular cylinder that has the height of A the same as the length of the side of a cube, and that cylinder has the same mass and density as the cube. Here we capture these requirements that are given in the problem statement as follows. The mass of the cube is equal to the mass of the cylinder, and rho, which stands for density, the density of the cube is equal to the density of the cylinder, which is to say that these two solids, a cube and a right circular cylinder, are made from one and the same material. From the previous episodes, we know that cylinders come in several different flavors. They could be circular, or they could be elliptic, and they could be right, or they could be oblique. And in this case, we're given a right circular cylinder, uniform density. That density is the same as the uniform density of the given cube. The height of the cylinder and the height of the cube and the size and the length of a side of a cube is the same, let's say a units of length. And we're asked, under all other conditions being equal, in near Earth gravity, in uniform gravity, near Earth's surface, let's say at sea level, which one of the solids is easier to tip over, all other conditions being equal. And again, physics is just like mathematics. There are no room for opinions. What we are looking for here is not a guess, is not an opinion, is not a wish. We're looking here for a solid proof. And yes, in physics, we generate proofs just like the same way in which we generate proofs in mathematics. And precisely in this problem, we want not only the answer. Again, in the big scope of things, in the physical community, nobody cares about the answer to this problem, but everyone cares about your ability to generate a solid reasoning, a solid justification, and a solid proof why the answer to that question is what it is, whatever it is. But we want to see a solid mathematical proof. To the best of my knowledge, there exists only one workable heuristic template or a plan of action or a miniature framework for solving this type of vague physics problems and for answering this type of vague physics questions. But if you know of any other or a better way, then please do not be shy. Feel free to share your knowledge with me. I'm always willing to learn new things. As such, if we are to answer a vague physics question or to solve a vague physics problem that is similar to the problem that we're given here as 2P1, we are to follow this here heuristic template shown on the board that has 5 steps. And ideally, especially when you present a solution to such a vague physics problem, then it is best or it is recommended to follow precisely these steps shown on the board over here in the order in which they're shown. 1, 2, 3, 4, 5, and do not hop around 2, 4, 1, 5, and 3, but present your solution precisely in that order: 1, 2, 3, 4, 5. Now, as a honest and realistic advice, the process of solving a technical problem, be it a problem in mathematics, physics, or computer science, is very hectic, chaotic. It's not really orderly as we describe over here. And sometimes, yes, we have to punch through this sequence and hop around it a little bit to see, okay, if we do this, then drill, 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 see if it works. Oh yeah, it works. Okay, I got it. Now I see what's going on, and we roll from the top to the bottom following the steps. Now, if we want to answer a vague physics question or seemingly solve a seemingly vague physics problem, as it is given in this case, S2P1, what exactly does it mean? Easier or harder? We are first, as the first order of business, to remove that seemingly ambiguous situation. We are to get rid of the not clear situation or something that is vague, and try to translate the spoken language notion given in the statement of this problem into a physics notion, which could be one or more physics notions. If we manage to do that successfully and we translated the given spoken language notion into one or more physics notions, then we are to move on to the second step, and only then we are to move to the second step of this template. In other words, it doesn't make sense to jump, for example, to the step number 2 or to step number 3 if we haven't addressed the step number 1, evidently. Now, once we have, or we think we have, some number of actionable physics notions, as the step number 2 of this heuristic template prescribes, we are to translate the language of physics into the corresponding language of mathematics. Let's say we successfully did that. Then, and only then again, it makes sense to move on to the step number 3 of this heuristic template, because again, if we do not have actionable mathematics, there is no point in trying to carry out the step number 3 and solve the underlying mathematics, simply because we do not have any actionable material to work on. But let's say we manage to translate the language of physics in this problem into the language of mathematics, then we move on to the step number 3, and at that point everything else recedes into the background. We forget about the spoken language notions, we forget about physics. What we have in front of us is a pure mathematical problem, and boom, the step number 3, we are to solve the resultant pure mathematics. Let's say we manage to do that. Then and only then it makes sense to move on to the step number 4 of this heuristic template, and that in that step we are to basically roll back steps number 2 and 1, basically fundamentally. In the step number 4 of this heuristic template, we are to take the solution of purely mathematical problem that we obtained in the step number 3, and we are to translate these mathematical results into the language of physics and into the notions of physics on which the mathematical apparatus worked. Once we did that, we are to move, and only then we are to move to the step number 5, and we are to take the physics notions that are explained by the underlying mathematics, and we should try to translate the notions and the results as they are looked at through the lens of physics back into the spoken language notions, in terms of which presumably the problem was stated to begin with. This step completes the circle, and we that way we solve this problem. Now, our viewers who tag along, they already see one peculiar property of the description of this template. And what is it? Correct. The total absence of technical jargon in the description of this template tells us that this template travels far and wide throughout the entire physics. Pick any layer or any branch of physics, and that heuristic template is applicable to the problem stated in the language of this physics layer or physics branch in equal measure. Statics, kinematics, dynamics, orbital mechanics, celestial mechanics, astrophysics, classical mechanics, relativistic mechanics, quantum mechanics, electricity, magnetism, ray optics, wave optics, thermodynamics, quantum field theory. You name your favorite branch or layer of physics, and if you have a seemingly vague problem stated in terms of that layer, the application of this here template to that problem may lead to your success. Now, the other thing is that is characteristic about this template is the following. As it is the case with all new ideas in hard sciences, whenever you come across such a new idea or a new something, that new something seems to be very big, very complex, very mysterious, and very important. But once you step up close and develop a close personal relationship with that something, you understand how it works, you understand the essence of that new something, and you put that essence into your bone marrow, then all of a sudden, miraculously, that new something, well, maybe it remains to be big, but it's not scary anymore and it's not important anymore. Such is the property of technical information in hard sciences. And in order to see how that template may be applied in practice, let us solve the given physics problem S2P1 precisely by following the steps outlined in this here heuristic template. Before we jump into the discussion of how exactly the first step of our heuristic template works, I would like to recommend to you guys to not worry too much about memorizing or writing down this template. By the end of this episode, if you solve this problem in physics with us using that template, you will have that template in your bone marrow already. That template is very natural, and you will zip through that template and run circles around that template with no effort unconsciously, and you will work very, very rapidly. As such, the purpose of the first step of our heuristic template of translating the given spoken language notion into one or more notions in physics is to precisely remove the seeming ambiguity and to remove the vagueness which by definition was introduced by the spoken language. And that step, in my humble opinion, is more of an art than the science for the following reason. The folks who have a reasonable or more than reasonable maturity in physics usually zip through this first step of our heuristic template very, very rapidly for the following two reasons. First, these people possess quite deep or tall, shall we say, vocabulary or arsenal of basic physics notions. Number one, they know a lot, let's say, about coordinates, velocities, accelerations, forces, linear momentums, angular momentums, torques, fields, Lagrangians, Hamiltonians, and on and on and on. That's number one. Number two, they have a good amount of experience in mapping. Let's say here we represent by a point a vague, let's say, spoken language notion, and these people have a good amount of experience in precisely mapping this vague spoken language notion to a best fit, notion or multiple notions in physics. And conversely, the folks who do not have much maturity in physics usually will fail, unfortunately, precisely at that step. For the newcomers to physics, this very first step is the proverbial graveyard, which is, let's say, littered with bodies of that students, I mean it in a good humorous way, meaning that precisely here many students, many newcomers to physics will fail and they will not be able to make any headway with the given problem precisely because do not they are not capable of carrying out that step for the following reasons. One, their vocabulary or their toolbox or their arsenal of basics helpful physics notions may not be that tall. They may not know uh, about many or enough physics notions, number one. But even if they do possess a reasonably sized vocabulary of basic physics notions, they may not have enough experience to precisely make that connection, make that map the given spoken language notion to the best fit notion or multiple notions in physics. And that is why they will fail over here. They will not be able to solve this problem. That is why I say that there is more art in carrying out this first step than it is science. It comes with experience. And again, do not worry too much if you were not able to solve this problem that we gave you completely correctly and on your own precisely because of this. If you were not able to do it, chances are high that you failed right here because you were not able to map or remove the ambiguity between what is easier and harder and the corresponding, even on the far end, the mathematics of it. So in this case, when we want to translate the vagueness or the seeming ambiguity introduced by the spoken language of easier and harder, what physics notion or what multiple physics notions can help us do that? Think on your own, put this video on pause, walk away, try to generate your idea, then come back and compare your idea to ours. Well, it turns out that the basic physics notion that removes the ambiguity and the vagueness introduced by the spoken language of this problem, easier or harder, is none other than I bought new chalk, guys, so I apologize if the chalk is not performing too well. So the basic physics notion that will help us unlock a correct solution of this problem is the so-called work, physics work. We'll designate it with the letter W. In different countries, in different times, different letters are used. Like in my time, for example, the work was designated with the uppercase letter A, but it doesn't really matter what we use to designate this or that physics notion with what symbol, as long as we understand the technical essence behind that notion. So here, physics work is a useful physics notion that will help us unlock a correct solution of this problem. And why is that? Well, first of all, like any basic physics notion, there is an unambiguous mathematics attached to such a notion. And in general, work is a scalar magnitude that in general is defined as a curvilinear integral or a line integral that is carried out over certain curve S, which is the product between the vector force and the element of the curve along which the material point to which the force F is applied is moving. And in this case, we do not worry about this scary looking thing. If you do not know anything about curvilinear integrals or line integrals of the first kind, we will not use them. The physics and the mathematics in this episode will be baby physics, baby mathematics, nothing complicated. This is following my paradigm that in order to explain a new idea, we use the simplest possible material, or the material that is as simple as possible, but not simpler. So everything will be baby physics, baby mathematics. Do not worry about it. We do not need that. Just as a general idea, one of the reasons why the basic notion of physics work will be helpful is because fundamentally, as every basic physics notion, there is a solid and unambiguous mathematics attached to it. And here, before we move on, I would like to say that there is, on the one hand, a seemingly reasonable connection between the idea of work as we understand it in everyday life without physics introduced, and the notion of physics work, or the notion of work in physics. We think that, okay, if something is hard to do, something is hard work, then numerically in physics, the magnitude of this scalar will be large, and conversely, if the work is easy, something is not that difficult to do, then the number attached to this here line integral of the first kind will be smaller. So there is a reasonable correlation. Easier, less work. Harder, more work. However, we have to be careful because at some point the mathematics of the underlying physics, as opposed to the real life situations, diverge. And it comes to when exactly conservative fields or conservative forces. For example, it is a possible definition of a conservative force, which is such that the work done by that force over the closed curve, for example, like so, is zero. The work is zero if it's carried out by a force applied to a material point, let's say that's moving in this, let's say, simple closed curve that does not have self-intersections, just like a loop. In this case, the work done by such a conservative force is zero. And another popular definition of a conservative force is a force for which the amount of work does not depend on the exact shape of the shape, but only depends on the original and the final configurations of the system. Now, let's conduct a very quick thought experiment, which actually you can do at home, and maybe you should do at home. Take two buckets, fill them with, let's say, 5 gallons of water each, 10 gallons total, 3.78 liters per gallon. So let's say we have 37.8 liters, let's say roughly 40 kilograms of dead weight in our hands. And then walk around the Olympic-size stadium on the inner track. That will be what? That will be 400 meters. So in terms of physics work done by the force of gravity, mg, applied to you, so let's say you weigh 180 pounds plus another 40, or let's say you weigh 80 kilograms, for example, or 90 kilograms, plus another, let's say, 40 kilograms of dead weight. So because the force due to gravity is conservative, the work done by that force around the closed path will be zero. So that's on the one hand. On the other hand, if we tell the person who actually was doing that, carrying these buckets of water for that much distance and with that much weight was zero, then the muscles in the body of that person will definitely disagree. Or the other way is, instead of running a closed loop circle over the Olympic-sized stadium with these two buckets of water, another very good exercise that's even more doable. Not everyone has access to the Olympic-sized stadium, but everyone has access to stairs. So let's go from the first floor, from the very bottom, from the first floor to the 5th floor. Go up the stairs with this 2 buckets, of 10 gallons of water, and then come down the stairs. Again, closed circuit. The work done by the force due to gravity will be zero because this force is conservative, and the corresponding integral will be zero. But if we tell that person who went up the 5th floor with 40 kilograms of dead weight and down that he or she did zero work, then again the muscles in the body of the person will strongly disagree with that statement. But what is the second reason why work is the basic physics notion that will help us solve this problem correctly? Well, the second reason is because work in this case is precisely the notion that addresses the heart of the matter. As Isaac Newton used to say, upon thinking about it, in the previous segment, we decided that a basic physics notion that removes the ambiguity of the spoken language notion given in this problem statement of easier to do or harder to do is the notion of work or physics work. We now think that it will be easier to tip over that solid for which it requires less physics works to do in order to flip it over, and conversely, it will be harder to tip over such a solid for which it is required to do more physics work in order to flip it over. But now we're coming closer to the idea of to understanding that we need to also resolve mathematically what does it mean to tip a solid over. What is the basic physics and what is the basic mathematics behind it? Well, that is the purpose of the second step, where we translate the identified notions of physics into the language of mathematics. And the way we do that is as follows. We will model, and this idea over here is so important that I wrote it on the board on the left hand side over here. We will model pretty much any given solid that we will be working with as the combination of two notions, of two ideas, if you will. The first such idea or notion is introduce a massless wireframe that captures the geometric essence of a given solid. For example, if we'll be working with a cube, instead of taking a solid cube, we will replace that solid cube with just a wireframe that is massless, but such a wireframe will exactly capture the essence of that solid. It will be a wireframe, a massless wireframe that represents a cube and not, for example, a tetrahedron or an icosahedron or a, for example, dodecahedron. This wireframe will represent the cube only, and nothing else. The second idea or the second notion of our model of a given solid will be the single and unique point that is located somehow in reference to the massless wireframe. And that single massive point will represent the center of mass of the entire solid. In other words, instead of dealing with the solid, we replace such a solid with a model. It is important to understand that we replace a physical solid that we will be working with a model that is constructed based on these two notions over here: a massless wireframe that captures the geometric essence of the given solid, plus the massive point that represents the center of mass of the original solid, not the massless wireframe, because this wireframe is massless. You see, that's the idea. But that center of mass, that unique point, represents the center of mass of the given solid. And now the next idea will be so important that I will be repeating it over and over again for many episodes in which we will be solving physics problems until you guys drive this idea into your bone marrow, and we will address that fundamental idea about physics by looking at this word over here, model. What do you guys think physics in general is? Or another way to put that question is, what do you guys think is the purpose of the computational work in physics? If in the previous segment I told you guys to not worry about writing down the steps of the heuristic template that we're working with, because by the end of this episode, you will put these steps into your bone marrow and you'll be zipping through them like there is no tomorrow. The deal with the idea that we're about to discuss is the opposite. I do recommend that you print out 159 copies of this idea in a very large font and hang it all over your house, in your bedroom, in your parents' bedroom, in your closet, in your bathroom, in your parents' bathroom, in the kitchen, in the living room, dining room, all over the place, so that you have it in front of you for many years to come until this idea eventually sinks in. But this fundamental idea that permeates the entire physics or the entire theoretical physics is the following: the computational goal of each and every computational work that is done in theoretical physics is to produce an exact solution of an approximate problem. As such, we can say that, parabolically speaking, and in a somewhat loose and jargonish but way of being faithful and of high fidelity, physics is an exact solution of an approximate problem. And this permutation of words, in other words, which specific word is attached to solution and to problem, can be changed. And in order to give you guys something to compare with, what do you think, as a short quiz? An approximate solution of an exact problem is what? An approximate solution of an exact problem is the purview or the computational goal of engineering, for example, mechanical engineering. When we design, for example, an internal combustion engine, that will be represented by an exact problem. We want a device that is an internal combustion engine, and the physics behind it, the burning of a fuel, the moving of the pistons in the cylinder, cranking the shaft, spinning the wheels and everything, represents an exact problem. But the solution of that exact problem will be approximate when we will be taking what's on paper and all these ideas that sit behind and ride on the, for example, thermodynamics, will be an approximation of our theoretical ideas that will be engineering. But in physics, we want to go the other way around, and we want to produce an exact solution of an approximate problem. Now, what is approximate problem over here is represented by? Think about it. And the correct answer over here is that an approximate problem, I will put a thingy underneath over here, and we'll write down what? An approximate problem represents what? An approximate problem represents precisely a model. You see, represents precisely a model. I will be in your face in a good way on pretty much most physics problem with that idea that physics is an exact solution of an approximate problem. And an approximate problem, we know already that it is a model. And what is a model? A set of assumptions which drive the following exact solution, because a model representing an approximate problem gives birth to mathematics, and then when we crank through this mathematics, mathematically we produce what? An exact solution of an approximate problem. In order to understand what it means that when we say that physics is an exact solution of an approximate problem, let us see how that idea works in this specific problem, S2P1. Now that we understand that physics is an exact solution of an approximate problem, and an approximate problem is represented by a model, which is a set of assumptions that leads to actionable mathematics, we apply this idea to our problem, and we agree that we will model a solid cube or a shape, massless shape that is filled with certain material of certain density and occupies certain volume with a combination of two things. What are these two things? a massless wireframe shown over here on your left hand side in blue chalk. The lines that are visible to us are shown in solid, and the lines that are not visible in a see-through cube are shown as dashed lines. For example, this line here on the left, in the back, and at the bottom over here are not visible. They're shown in dashed line. And what is the second idea or the second notion? A single massive point that represents the unique center of mass of that solid. And without getting too technical about it, this single unique point that represents the center of mass is again a mathematical model of a point in which the entire mass of the given solid is gathered in such a way that if we take this solid near Earth gravity in uniform gravitational field, hang it, suspend it on a thread that is connected precisely to that point, then this solid, or this cube in this case, will have zero tendency to move or to rotate, to spin, or change its position in any other way. And also, it is important to understand that both of these things have to be present at the same time. In other words, our mathematical model of a solid is a combination of two things that is transactional, both or none. If we just take a massless wireframe without the center of mass, it's not very helpful, because we want to know where is that center of mass that represents the entire mass of this particular shape, whose geometric essence is captured precisely in this wireframe. In other words, this wireframe captures the geometric essence of a cube and represents a cube and nothing else, no other solid. Conversely, just with one massive point that represents the center of mass of some mysterious shape that floats by itself in the greater beyond without the corresponding massless wireframe attached to it is also not helpful. In other words, a massless frame that does capture the geometric essence of the given shape by itself without the center of mass is not helpful, and just the center of mass as a massive point that floats in the greater beyond without the corresponding massless wireframe that captures the geometric essence of the shape of the given shape also is not helpful. It's when two things come together, the massless wireframe that captures the geometric essence of the shape plus the unique center massive point that represents the center of mass of the corresponding solid, this combination does become helpful. And once we understand that, we can now address the following question: what is the mathematics of this tipping over? What does it mean to take a solid and tip it over? Now, before we move on, don't forget that we're still within the realm of the second step, where we are translating the physics notion, the helpful physics notion of physics work into the underlying mathematics. We're getting to it in stages, and that is what we will do next, when we will translate the idea of tipping over into solid and actionable mathematics. Now that we all understand the business of physics, an exact solution of an approximate problem, model, set of assumptions, we're still deep in the bowels of the second step of our heuristic template, when we're trying to translate the actionable physics into actionable mathematics. What is, first of all, the physics of tipping over? Well, we're told that our cube, our solid cube, is of uniform density. That means that we know the exact location of its unique center of mass. It can be, for example, located by constructing two diagonals of the cube, shown over here, this diagonal and this diagonal. These two diagonals will form a certain plane, which we will discuss in a few seconds. And in that plane, at the intersection of these two diagonals of a cube, will be exactly the center of mass of that cube. And now all the ideas begin to unfold as we think about the physics of tipping over. So if we know the location of the center of mass of our cube, O, the point O, then to that point we apply the force due to gravity mg with the green vector pointing where? Technically downwards, but more technically perpendicularly to the spherical surface, which is another model of Earth, spherical surface of Earth towards the Earth center. This is where the vector mg points to. And let's say our cube is resting on a table on its bottom, here on its bottom face. Then what will happen if we will construct the straight line through the vector that is the model of the force due to gravity mg? Well, the straight line and the base plane will intersect, and when a straight line intersects with the plane, they do so at a single point. So that will be, let's say, the point P, the projection of the, let's say, vector onto that plane. And let's say now we start approaching the idea of tipping over. What is tipping over? Well, let's say we fix this side of the cube, this side over here, the right side of the cube, and we apply very, very, very tiny, very small force to the point O, to the center of mass of that cube, which is a model of a solid. Well, in this case, we will say that the cube is in the state of stable equilibrium. It will not have any tendency to move. It will pretty much stay where it is. But as we take our cube and we will try to, as we fix the one edge, we will fix one edge of the cube to a table, let's say, we try to flip it over with respect or via its edge, like so, like this, so that you guys can see. This is how we will try to flip over our cube, like this or like this. You understand what's going on. As we try to flip our cube over its edge like so, what will happen? Well, if we repeat the same exercise of projecting over our vector that models the force due to gravity mg, I did not show mg over here, but you guys understand mg, I do not want to introduce more clutter than I have to, then over the tilted cube, this vector will intersect the tilted plane of the tilted base or bottom plane of the cube at a different point P, not the original one. The original one will be the dead center of the base face or the bottom face. Again, two diagonals of the base face will intersect at that point. But here, the point P will be painted. Let's say we shine a laser light. And here, guys, I prepared a little model for you so that you can understand what is going on. Let's say our vector is like this. So applied to the center of the cube in the stable state, in the state of stable equilibrium, the vector will point, it will always point perpendicular to the Earth's surface, to the Earth's center. But once we begin turning or trying to flip over our cube with respect to one of its edges, the right edge in this case, the vector that, let's say, it is attached to the center of mass in a pendulum-like fashion. So it can swing like so. Do the math, do the physics, just kidding. So here, in the state of being flipped over, you can see that even though the vector mg will still point downwards technically, the projection of that vector onto the base face of the cube will change. Now it will move and it will paint a different point on the base of that cube that will be distinct from the original point to where the vector mg projected in a state of stable equilibrium, but that point will still be strictly within the base or bottom face of that cube. But we see the tendency. What is the tendency of that point? The tendency of this point is to approach this fixed edge over which or via which we're trying to flip our cube or tip it over, as the problem statement demands. Now we come to the physics of flipping over. At some point, our vector mg, due to the force of gravity over here, mg, will fall precisely onto the edge of the cube that is being flipped or tipped over via one of its fixed edges, it will fall precisely, or its projection will fall precisely on its edge, or that vector, parabolically speaking, will paint a point precisely, the point be precisely on the fixed edge with respect to which we're trying to tip that solid over, precisely on that point. Now that that point slid all the way onto the fixed edge of the cube, we understand what? Now we can say that the cube is in the flipped over state, because at this point it is in the state of unstable or not stable equilibrium, and very, very small, tiny forces applied to the center of mass in that state will make this cube move a lot, or let's say violently. Here at this stage, if we, let's say, apply a small, infinitesimally small, or very, very small, tiny force to the center of mass, our cube will, or let's say we just stop acting on the cube, it will slam back on the table. It will slam back on the table and go back into the state of stable equilibrium, you see, like so. But when it is in the flipped over state already, then it is not really entirely clear which way it will go. It may really tip over and flip to the other side, or it can slam back on the table and take its original state. But at this point, we will agree that when the projection of the force due to gravity, as it is applied to the center of mass of the given solid through our massless wireframe model, falls precisely onto the fixed edge, then and only then our cube or our solid is in the flipped over state. So now this is the physics, and again, I recommend that you guys do the same thing, play with the same model. The vector that models the action of the force of gravity as it is applies to the center of mass, pendulum-like fashion. I will try to hypnotize you. Do the math, do the physics. And then once you begin flipping over your cube, that vector due to the force due to gravity mg will begin approaching the edge, and bam, when it falls precisely onto the fixed edge with respect to which we're trying to flip over the cube, then game over. We have reached the flipped over state of our cube. Game over. And now that we understand the physics, of the flipping over process, remember, we're still in the bowels of the second step. We're trying to translate the physics into mathematics. What is the mathematics of the flipping over business? Well, you should be able to see. We will discuss it in a few seconds in the next segment, but for those who did not solve this problem completely correctly and on your own, use this as an opportunity to do the right thing, practice physics correctly, put this video on pause, walk away, generate your idea. What is going on mathematically with the center of mass O? Well, the correct answer is that the center of mass O is being actually rotated about the fixed edge of the cube. And it is being rotated where? It is being rotated up. So this is precisely what it means when we say that the work, the physics work done by the force of gravity as it is applied to the center of mass of a given solid is done what? Is done against gravity. In plain English, what we're trying to do when we're flipping over a cube or any other solid, we are lifting it, or we're making work, we're doing work by lifting the center of mass of that solid at hand in a certain way. And what is the mathematics of this lifting up? Well, we'll discuss it in the next segment, but now you guys already should understand that a cube that sits in the state of stable equilibrium can be flipped over what? Can be flipped over via one of its edges, like so, when the edge is fixed, or we can also flip a cube over via what? One of its vertices. That is a different motion, and we'll cover two cases, but now we see that we have two opportunities with the cube. Flip it over via one of its edges when the edge is fixed, or flip that cube over via one of its vertices when a vertex of such a cube is fixed. And the mathematics The mathematics of this flipping over business is the following one. Awesome. Now that we understand the physics of this tipping over business, let us solidify our understanding of the underlying physics with the corresponding mathematics, because remember, this is the essence of this stage number two. Stage number two of our heuristic process is to convert the relevant notions of physics or the language of physics into the corresponding language of mathematics. And now we all should be able to do that. This is not that complicated. That is, we now know that the center of mass of our uniformly dense cube that is modeled with a massless wireframe shown in blue and a single massive point O that represents the center of mass of that uniformly dense cube must be rotated through the angle alpha, which is what kind of angle? That is the angle that is formed by the corresponding diagonal plane A, B, C, D. I cross-hatched that plane for you guys with vertical blue lines. You can see this is the plane that must be rotated from the state of stable equilibrium, from the initial state in which all the uh, solids under investigation must be in their initial state, and that plane must be rotated through that angle alpha into what position? Into a strictly vertical position. We go from this initial position, bam, into the strictly vertical position, and this is precisely the angle alpha shown here in yellow, if you guys can see that. This is the angle between the diagonal of the front face of our cube and the edge, the corresponding edge. If we fix the edge AB, it sits on the table like so, and with respect to that fixed edge, we are trying to flip our cube over. Let me show it to you guys one more time. Let's say this is our cube. We fix this edge right here to the table. Our cube sits on the table, and then we're trying to flip over our cube or tip over the cube like so, via or with respect to a fixed edge like so. And again, as we explained, once we place it into a position where the corresponding vector that models the force due to gravity that is applied to the center of mass of the cube projects directly onto or paints a point directly, as you saw on the right hand side of your screen a few seconds ago, on that edge with respect to which we're trying to flip over our cube. So as we rotate this diagonal plane ABCD that contains precisely the center of mass of our uniformly dense cube, we will rotate that plane. In this case, it will be what? It will be clockwise through the angle alpha from its position in the state of stable equilibrium into the flipped over state, which means strictly vertically in this case. And that point P will jump on the edge with respect to which, the edge of the cube with respect to which we're trying to tip the cube over, and we reach the state of tipped over, because after that, that's it, game over for that cube. So what is the mathematics of that tipping over business? Well, if we look at our cube from its front like this, I captured this view over here on the right hand side of your screen. We essentially have the front face of the cube. The vertex O is this guy. The vertex O is this guy, because we turned the cube over and we're leveled with it. The point B is hiding behind the point A. You cannot see it. The diagonal AD is precisely this guy. This is the diagonal AD. You see, diagonal AD, diagonal AD, angle alpha through which our diagonal plane ABCD must be rotated. This is the angle alpha. This is the angle that is formed by the diagonal of the front face and the corresponding vertical edge of the cube. It will be this edge right here, this edge right here. No mystery. So what is the mathematics of this tipping over? If the cube is tipped over from the initial state of stable equilibrium, then the point O, the center of mass of this uniformly dense cube, will be rotated. Technically, if we drop, let's see if I can make even more mess over here. If we connect the centers of the edge DC and AB, like so, then this will be the point onto which the point O will be projected. This will be an orthogonal projection on the edge AB. And then technically, with respect to the straight line AB through this point over here, we will be rotating the point O, the center of mass of our uniformly dense cube, upwards, and we will be lifting that center of mass upwards and doing work against gravity. And now it's a competition. Is it more work that needs to be done by the force of gravity as it is applied to the center of mass of the cube is more by magnitude than the same work that must be done by the force of gravity applied to what? To the center of mass of a uniformly dense right circular cylinder in order to tip that cylinder over. This is the competition. This is the game. We have two horses in the race. So that means that the point O is rotated like so, clockwise, through the angle alpha, and it is taken into the position O prime shown over here. The length of the side of each edge of our cube is A. The angle is 90, everything over here lengthwise is A. So what do we do? Again, we remember that because this time we capture the work done by the force due to gravity. There is no kinetic energy associated with this situation. In the initial state, the velocities of everything is zero. In the final state, the velocities of everything is zero. We're only interested in the work done by the force due to gravity. And we remember that the initial level with respect to which the value of the potential energy will be zero is arbitrary. We can take it anywhere. We can take it passing through the point O like this, or we can take it passing through the base. I'll take it passing through the base just because we have natural reference in a sense that our let's say our cube is resting over here, is resting on a table. Let's pretend this is a table. So with respect to this level over here, on which the bottom face of the cube rests in the state of stable equilibrium, this is zero potential energy. So U is equal to zero right here. This is the guy. This is the table. So what are we doing here technically? On the one hand, we are rotating the point O with respect to the point A by the angle alpha formed between the diagonal of our square and the right edge into the point O prime that must sit on this edge over here of the cube. And on the other hand, remember that the force due to gravity is what? It's a conservative force. The actual trajectory, that the point to which that force is applied, is irrelevant. The shape of the trajectory does not make any difference. The only difference, the only things that do matter is what? Is the initial position and the final position. So the difference in height over here, which I captured with delta H cubed, is precisely what captures the mathematics of the tipping over business. So you see right now we succeeded in translating the relevant notions of physics into the language of mathematics. It is this delta H, the difference between the distance from the point A to the point O prime and from the point A to the point H, this delta H is what counts. And now we have two horses in the race. It's a race between the work that is done by force of gravity against we're lifting something up. That is when the force is applied to the center of mass of the uniformly dense cube versus the same force applied to the center of mass of what? Uniformly dense right circular cylinder. We'll talk about this in a second, but this point over here captured as O. The destination is O prime. So technically the point O prime is what? It's a rotational image of the point A. And now in the next segment, what will we do? Well, if we agree that the point V over here is the vertical projection of the center of mass O onto its base, and the point H over here is the horizontal projection, if you will, this way onto the side of the square. Then with this setup, the magnitude of the delta H cube has been designated, but now what is the mathematical program? What do we need to do? What's the mathematical challenge? Well, the mathematical program here is to express this delta H of cube and later on delta H of right circular cylinder through the locally available material. And what is the locally available material? Well, the locally available material is the magnitude that we're given A for the side, for the length of the edge of a cube and the height of a right circular cylinder. And what else? And the actual geometry of the mass that we're trying to tip over. A few seconds ago, I made a typo. I apologize to my viewers. I said that the point O prime is the rotational image of the point A. Clearly, that was a mistake. My bad. The point O prime is evidently the rotational image of the point O, the point A over here being the center of rotation. Because rotation of the plane is a rigid transformation, it means that the distance from the point A to the point O prime will be exactly the same as the distance from the point A to the point O. As such, now that we have established our mathematical program, we're moving on to the third step of our heuristic template or miniature framework or a plan of action. And now we just have to express the magnitude of delta H cube shown over here on the right hand side of your screen in yellow in terms of the locally available material, which is the length of the side A, and the known geometry. You see the known geometry of the mass that is being tipped over. To that end, recall that the amount of work that is done in case of the cube, by the force due to gravity in order to lift the center of mass O, into the point O prime, O to O prime is what? By definition, it's the magnitude of the potential energy of that point. We will measure it with respect to the base of the cube, but you can measure it with respect to this plane or any other plane, it doesn't matter. So here we will write down mg times the distance from the point V to the point O minus mg, that's the initial state, and the final state, mg times the distance from the point A to the point O prime. Now, I do not qualify the mass in this case. Why? Because we're told that the mass of the uniformly dense cube is exactly the same as the mass of the uniformly dense right circular cylinder. That is why it's m all over. And which way we can rearrange this expression over here? Well, mg is the multiplicative constant, the mass is constant, the acceleration due to gravity is constant. It can be factored out. Let's do that with the negative sign. And then this will be the distance A, the distance AO prime minus the distance VO. That much should be understood. We simply carried out, factored out the negative sign over here. This factor comes out to be with the positive sign, and this distance comes out to be with the negative sign. And now it is pretty much game over. Let's think about it. The distance from the point V to the point O, the distance from the point V to the point O is exactly the same as the distance from the point A to the point H. This is due to our constructions. The angles over here and over here are right. The distances are all over are the same. A over 2. That means that this distance over here, let's write it down maybe this way, it will be a over 2. Now let's discuss this distance right here, a o prime. Like I said before, since the rotation of the plane is a transformation that is rigid, which means that it preserves the distance between any 2 points before, during, and after the motion. That means the distance AO prime is the same as the distance AO. And what is the distance AO? Well, if the distance AO multiplied by the cosine of this here angle, what do we get? We get the distance AH. So that means that the distance from the point A to the point O, which is the same as the distance from the point A to the point O prime, will be what? This distance will be, let's designate it here, that distance times the cosine, so A over 2 cosines of the angle alpha. That's the distance. A over 2 can be factored out, times A over 2, open paren, 1 over cosine of the angle alpha minus 1, and this is it. This is the expression for the amount of work that is needed to be done against gravity in order to rotate the center of mass of our uniformly dense cube from its position of stable equilibrium, when it rests on a horizontal, let's say, table on a horizontal plane, into the point which corresponds to the state when the uniformly dense cube is tipped over. I'll take a few seconds right now to erase the board, but this is the expression, this is the expression that we want to keep. I'll write it down separately because next we will derive a similar expression, but for a right circular cylinder. Here is my incredible simulation of a right circular cylinder. I have all sorts of knitting supplies, so ignore the man behind the curtain as it makes a noise, but the idea here is the following. The base and the top, the base and the top of a right circular cylinder is what? By definition, it's a circle. The other flavor of a similar type of cylinder will be what? An elliptic cylinder, which means that the base and the top of such a cylinder will be an ellipse. So here an ellipse already is not a completely symmetrical figure as a circle. So with the circle being the base and the top of a right circular cylinder, when we decide to tip such a cylinder over, we can pick any point on its base with respect to which we will be flipping that cylinder over. As such, let's say in that particular view, we have our cylinder, right circular cylinder, resting on a horizontal plane, resting on a table, let's say. And then with respect to any one of its points, we decide to try to flip it over. We already understand that the physics of this flipping over business is exactly the same as long as the projection of the vector, that is the model of the force due to gravity, falls strictly into the circular base, then the right circular cylinder is not tipped over. But the moment that vector paints the point precisely on the point with respect to which the cylinder is being tipped over, then this is it, game over. We consider that right circular cylinder to be in the tipped over state. Basically everything that we said about a uniformly dense cube applies to this here uniformly dense right circular cylinder. The physics and the mathematics are exactly the same. The only difference now is in the specific parameters with in terms of which we capture the amount of work that is needed to be done against gravity when the force of gravity is applied to the center of mass of a uniformly dense right circular cylinder in order to take it from the position where the cylinder sits on a horizontal plane into the state which corresponds to the state of being tipped over. Everything is exactly the same. The physics and the mathematics is the same, but now what do we have? If we cut our cylinder with a plane that connects the diametrically opposite points at the base and at the top, we cut it like so, then what will happen? The analog of the ABCD plane, the diagonal plane in the cube, will be what? Well, technically this will be an elliptic plane, let's say. And then in order to tip that uniformly dense right circular cylinder, to tip it over, we will have to lift that plane again into strictly vertical position, like so. And then with that motion, when we tip over a right circular cylinder, what will happen? Its center of gravity again will be lifted. The work will be done against gravity. That's why we saw the minus sign in front of our calculations in the previous segment, but we're actually interested either in the absolute value of this work, or we can construct a ratio to eliminate all the pesky minuses. So that is the physics and the mathematics of tipping over a uniformly dense right circular cylinder. That much should be understood. It's very straightforward. And here I cross-hatch that plane that needs to be lifted into a strictly vertical position here in green. But if we cut our cylinder with a strictly vertical plane, like so, through the center of that right circular cylinder, what will happen? Well, here we will get a rectangular cross section, and this rectangular cross section is shown over here. The height, remember that we're told that the height of our right circular cylinder is what? Is the same as the length of any side of our cube. So we make this linear size comparable between the right circular cylinder and a cube. So this distance over here, let's say the height of our rectangle or rectangular cross section of a right circular cylinder through its center will be A. The length of that rectangular cross section will be what? Will be twice the radius, twice the radius. Let's say this is the radius. So this distance will be twice the radius, and then the rest of the mathematics actually will be identical to the mathematics that we saw just a few seconds ago when we worked with the cube, except that in the previous segment we had a square, and now we will have a genuine rectangle. Now, at this point, I hope that some of our viewers at least see that now is the time when we reap the benefits of studying mathematics first. What do we see across these two segments? Well, we see that we studied already the problem-solving approach in mathematics called reduce and conquer. Remember, we dedicated several episodes to the study of this problem-solving approach, and that approach prescribes what? If we cannot solve the current very difficult problem, we should try to keep the technical essence of that difficult problem, but reduce it in series of steps to a simpler problem that we can solve. So in this case, if, for example, dealing with a right circular cylinder or a cube is too difficult, some of our viewers hopefully realize that, okay, how about solving a similar problem but in two space? We have a square, we need to flip it over, or we have a rectangle, we have to flip it over. Which one is easier to flip over or tip over? So here the arithmetic will be exactly the same. 1/2 of the diagonal, let's say if this is our favorite point A, this is our favorite point A, the rest of the arithmetic is identical. The distances will be slightly different, but essentially the fundamental approach will be exactly the same. The delta H of a cylinder, shown on the right-hand side of your screen over here, will have exactly the same expression. Everything will be the same. The expression for the amount of work will essentially be the same, but instead of the cosine or the value of the trigonometric function of cosine evaluated at the angle alpha that we saw in case of the square. Here we will have the cosine of the angle beta, and that is the angle between this diagonal, or this straight line right here. This straight line is shown over here, and this side of the rectangle, but all this half business is exactly the same. Half of A, and this is 1/2 of the diagonal. This is it. Now the question is, what is the value of the radius of our cylinder? Well, we are told that the mass of the cube, which is the density of the cube, times its volume, which is a cube, must be equal to, that's what we're told in the problem statement, the density of the cylinder times what the height of the cylinder, a, times pi r squared. What does that mean? And this expression over here represents the mass of the cylinder. Here I use the middle school fact that you guys should remember. Mass equals density times volume when everything is uniform. No integrals over lines or over volumes or over surfaces. This is a baby formula that connects the mass, the constant density of the matter from which this mass is comprised, and the volume of that mass. So here the densities cancel out. One copy of A cancels out. So what do we have for the magnitude of the radius? It will be, the radius will be what? A divided by square root of pi. This is our radius. So now we should remember this, memorize this, chalk it up to the corner of your memory or write it down. This is the relation that we will need very soon. But now that this is all understood, we have all the ducks in a row to write down our expression for the amount of work that is needed to be done against gravity in order to tip over our uniformly dense right circular cylinder. We will write this expression for cylinder, but everything else will remain the same. The center of mass O needs to be lifted into the position O prime, as shown over here. O to O prime, rotation through the angle beta. In this case, clockwise relative to the point A. A is the point of rotation. The distance AO prime is the same as AO. AO times the cosine of the beta will be A over 2. So the distance AO will be what? A over 2 copies of the cosine beta. So here we will have the expression, which one? Minus mg A over 2, 1 over cosine of angle beta minus 1. And this is it. And what did we have for the same, the expression for the same amount of work that was needed to be done in order to tip over a uniformly dense cube? Well, it was the same, except here we had the angle, what? The angle alpha. Now, for the angle alpha, it is straightforward to see in your mind's eye what? For the angle alpha, tangents of alpha will be what? It's exactly 1, because the angle between any one diagonal of a cube, and this is A, this angle is pi over 4, or 45 degrees. The value of the trigonometric function of tangent evaluated at pi over 4 is 1. Now, what can we say about the angle beta? Because now, remember, now we have two horses in the race. We need to somehow get a grip, get a computational grip on these angles, because now we need to compare two expressions. The second expression is what? Minus mga over 2 open paren 1 over cosine of alpha minus 1 close paren. These are the two expressions that we have to compare. Now the tangent for the angle beta will be what? In complex analysis, we will be defining this function most likely as a power series, which is a product between sine of the angle and 1 over cosine. But here we will use the middle school definition in terms of right triangles. What is the value of the trigonometric function of tangent using the middle school definition of tangent through right triangles? Well, this will be the ratio of the lengths of what? Of the opposite side, 2r, to the length of the adjacent side, which is a. But remember, we know what r is in terms of a. So this will be what? 2a over square root of pi. And here is a. A and a cancel each other out. So the tangent of the angle beta will be 2 over square root of pi. And now, let's say you understand everything what just transpired over here. I will write down over here, I will erase this. I hope this is all understandable. It's nothing complicated. Again, nothing beyond baby middle school arithmetic for the tangents. And then once we understand that, let us construct the ratio between. Let us construct the ratio now that you understand what is going on with this expression, where it came from. It's basically more of the same. Essentially, this is the same situation, except that instead of a square, we're dealing with a rectangle whose parameters are well known, and boom, rotation about a through the angle beta. This is all to it. So the ratio of the work done in case of a cube by rotating O into O prime, to the work done by a cylinder by doing essentially the same thing, lifting, will be what? If we do the arithmetic right, it will be what? 1 over 1 minus cosine of alpha divided by 1 minus cosine of beta times cosine of beta divided by cosine of alpha. You see, this is the ratio of these two works, and the answer to which way it goes, less than 1, greater than 1, or equal to 1, will answer the question, because this is how we framed our answer. And we will do the analysis of this here relation in the next segment, which, by the way, shows that if you want to do physics, then it is beneficial to know as much mathematics as possible. Depending on your level of mathematical maturity, if you are doing this, for example, in middle school, then you will have to take what follows at its face value. But if you learned some amount of real analysis, or you're doing it later in your educational career, then you probably most likely did take a course in real analysis, and most likely you have generated the proofs of all these statements yourself. So here we'll need the following. The single variable real-to-real function square root of x is what? Is continuous and is monotonically increasing on the positive branch of the real axis. When the values of its independent argument grow, so are the values, as shown with a partial graph over here. The trigonometric function of tangent on the subset of real numbers from 0 to pi over 2, we're interested only in this little segment over here, is also what? Continuous and is uniformly increasing. I'm sorry, not uniformly. monotonically increasing. So here we're interested on the range of angles between 0 and pi over 2, as it is evident through the geometry of this problem. And lastly, as it is shown with the partial graph, the vertical straight line x equal to pi over 2 is what is one of the vertical asymptotes of this graph. The graph is partial, evidently. Now, the trigonometric function of cosine on the same subset of real numbers from 0 to pi over 2, is continuous, but it is monotonically decreasing. Here, the functions monotonically increase when the independent arguments grow. Then the values of these functions grow here and here, square root of x and tangent. When the values of x increase, or when the values of the angle increase, so is the tangent will increase. Here, however, the situation is the other way around. On the subset of real numbers from 0 to pi over 2, the trigonometric function of cosine is continuous, but is monotonically decreasing. I apologize again for these graphs. These graphs are just for demonstration purposes. They're hopelessly out of scale and out of proportion. I do this just to drive the point home. So here, as the values of the corresponding angle increase, the values of the corresponding function of the cosine decrease. So now, where do we start our analysis? Remember, 1 minus cosine of alpha over 1 minus cosine of beta times cosine of beta divided by the cosine of alpha. So here pi is less over 4. We agree on that much. Pi is less than 4. For the reasons that I explained, precisely because the single variable real-to-real function, square root of x, is continuous and is monotonically increasing. If pi is less than 4, the corresponding values, square root of pi will be less than square root of 4. 4 is a perfect square. Look at that. Square root of pi is strictly less than 2. And what does that mean? If we divide both sides of this inequality then by one and the same positive real number, what will happen? Nothing bad will happen. This sign will stay the same. So 2 over square root of pi will be strictly larger than 1, you see. And this is what? Well, this is the tangent of the angle beta. And what is the tangent of the angle alpha? 1. Tangent of beta, tangent of 1. So if the values are larger, we go the other way. The corresponding angles are larger. So what can we say? The angle alpha, in this case, is strictly less than the angle beta. This is the conclusion we draw. Step once more to the right. If the angle alpha is strictly less than the angle of beta, then due to continuity and monotonically decreasing behavior of the trigonometric function of cosine, what can we say about the relationship between these two cosines? Well, it means that the cosine of alpha, actually, in this case, cosine of alpha will be what? Strictly larger than the cosine of beta. You see, this is a quick analysis. Again, once you have enough of knowledge of mathematics, you will zip through this computation in a second or less. I show this analysis in slow motions. I play it in slow motion for the benefit of all the viewers on our channel. This is how things are done by the book in a way. This is the underlying mathematics. Again, this is baby physics, baby mathematics, but when you will be presenting your solutions to much more difficult problems, if you showcase your steps, I'll have to say a few words at the end. The arbitration and the refereeing will be very straightforward. So now we have that. So what does that mean? Let's play with this relationship over here. Well, if we divide both sides of this relation by the cosine of alpha, which is, again, see here, it's strictly positive. So the sign will remain the same. So the cosine of cosine of beta divided by the cosine of alpha in this case will be what? Strictly less than 1. Would you agree? So one factor, remember one factor that we had, we already took care of. Now, let's do this, the final step. Again, the reason I play all these deductions in slow motion so that all the viewers on our channel tag along and understand what came from where, but evidently if you skip these details, you should be able to reproduce them on demand with half a crank. So now we already established that the cosine of alpha is strictly larger than the cosine of beta. We proved that much. If we multiply this relation by -1, what will happen? What will happen is that the sign in this strict inequality will have to be flipped. Minus cosine of alpha will be smaller than, less than, minus cosine of beta. So far so good. Now we tack on one and the same positive real number. 1, 1. What's going on here? The relationship will stay the same. And if we divide this inequality by one and the same strictly positive real number, why is it positive? Well, cosine of beta in this case is strictly less than 1. You see, everything is fine. So here we take this out, and what do we write? Divided by 1 minus cosine of beta is strictly less than 1. A real number that is strictly less than 1 times another real number strictly less than 1. 0.7 times 0.8, 0.56 or some such. So the result is strictly less than 1. And what does that mean? It means that if we are to carry, we're still in the bowels of the third step. We're almost done. We're almost done. But just to be good citizens of mathematics, what do we need to write over here? We need to write that mathematics has a good dollar on the fact that the work done by a cube by lifting its center of mass into the tipped over state to the work done by a cylinder, we're doing essentially the same thing as what? Strictly less than 1, period, the end. This is where the mathematics ends. Remember, right now what we were doing all along is a strictly or pure mathematical analysis of the situation. We don't really care about anything else. Like I said before, everything else recedes into the background. Mathematics steps over on the stage. It becomes the first-class citizen, and mathematics in isolation of everything else says what it has to say. And this is, let's put this in a little box. This is where mathematics ends. This is where mathematics ends, and we are ready to move where? Onto the fourth stage of our heuristic template. Very nice. Now we're done with the step number 3. We're moving on to the step number 4. So we translate the underlying mathematics, the results that we obtained by doing nothing but pure mathematics, into the corresponding language of physics. Into the language of physics, and that part is very straightforward, nothing complicated here. Mathematics doesn't care what the symbols are. Mathematics did what it did in total isolation from the underlying meaning. This is, by the way, quite a deep idea, and it ties into the next problem-solving approach that we will be studying, the method of problem-solving approach of mathematical equivalence. We will see what that entails, but here we simply take the mathematical result and wrap it or unwrap it, depending on how you want to phrase it, dress it up into the language of physics. And what do we state? Well, we state that it takes, if you want to write in terms of absolute values, you will write that the absolute value of the work of the cube is strictly less than the absolute value of the work in case of a cylinder. But stepping from mathematics back into the land of physics, we will have to say what? If a uniformly dense cube is tipped over via one of its edges, then it requires less work to tip over that cube that way than it is required to tip over a comparably sized, uniformly dense right circular cylinder. That is the answer. More physics work is needed in order to tip over a uniform right circular cylinder than it is needed to tip over a uniformly dense cube, comparably sized, when the cube is tipped over one of its edges. And now that we're done with physics, we can go back and execute the last step in our template and translate the language of physics back into the spoken language. Now that we translated the relevant mathematics into the language of physics, we close the circle and finally answer one of the questions that was posed in this problem by translating the relevant physics into the spoken language notions. That step is straightforward, but still we need to say what? We need to say that less work, less physics work, let's be pedantic about it, less physics work translates into what? Easier. Translates into easier. This is the basic idea when we translate the underlying physics into the notions that we used in the spoken language. This is our reverse translation or reverse mapping, if you will. Less physics work translates into easier. More physics works translates into harder. Consequently, the answer to the question that was posed in this problem is the following. When and if a uniformly dense cube is tipped over one of its edges, then it is easier to tip over that cube than it is to tip over a comparably sized, uniformly dense right circular cylinder that has the same height. And that covers that piece. And in the next segment, I will move much faster and I will cover the case when our favorite cube is tipped over not one of its edges, but it's tipped over one of its vertices. This is a perfect opportunity for those of our viewers who were not able to solve this problem correctly, completely, and on their own to put this video on pause. Once you understand what is going on, we suggest that you go do your computations on your own and then come back and compare your results to ours. And here in the public setting, I will analyze the case when our uniformly dense cube is tipped over with respect to one of its edges, like so. I'm sorry, one of its vertices, not edges, but vertices. We flip over, we tip our cube over with respect to one of its vertices. Let's say this will be the vertex A. In this case, what do I have to do? Well, in this case, again, there will be another plane A, B, C, D, the rectangular plane. The height of this plane will be what? The length of the edge of a cube A, and the width will be what? The length of a diagonal, A times square root of 2. And we have to rotate the center of mass of our uniformly dense cube into a position somewhere along the edge that delineates the vertex with respect to which the uniformly dense cube is being tipped over by. And by doing so, we will rotate the center of mass through the angle gamma this time. I decided not to call it alpha as we did in the first case. Let this angle be gamma just to be distinct. So when we tip our uniformly dense cube over via one of its vertices, such as the vertex A, we will have to rotate the diagonal, see this diagonal of our cube, through the angle gamma until this diagonal is taken strictly into a vertical position. Now, the rest of the arithmetic, again, because here there will be another rectangle, and the rest of the arithmetic will be exactly the same. So the ratio of the works or physics works that need to be done in order to rotate or lift the corresponding center of mass of a uniformly dense cube and of a uniformly dense right circular cylinder will be exactly the same. I highlighted the angle gamma for you guys so you can see it in red. So what can we say about how do we analyze this case? Well, the rectangle, the triangle, let's give it names A, let's say this point is B, and let's say this point is C. So the triangle ABC is what? Of course, it is a right triangle. The interior angle over here, the magnitude of this interior angle is pi over 2 radians, 90 degrees. So very, very straightforward manner. What do we have? For the tangent of the angle, where's my red chalk? For the tangent of the angle gamma, what do we have? We have the length of the opposite side, a times square root of 2, related to the length of the adjacent side, a. So this is what? This is square root of 2. It's that plain simple. So now the race is between this magnitude and 2 over square root of pi. Remember, this is our tangent of the angle beta from the previous segment. What is the relation over here between these guys? Well, you can reason as follows. Let's say we definitely know that pi is greater than 2. That much we know. The inequality here is strict. So multiply this relation through by one and the same strictly positive real number, 2. 2 times 2, 2 times pi. So 4 is greater than, 4 is strictly less than 2 over pi. And again, our square root of pi, single variable, real to real function, square root of x, continuous, monotonically increasing, yada yada. You already know the drill. If we take the square root, so what will it be? The relation will stay the same. 2 is less than square root of 2 pi. And what does that mean? That means that square root of 2 is strictly larger than 2 over square root of pi. Again, continuous, monotonically increasing, tangent. This is the tangent of the angle beta. This is the tangent of the angle gamma. That means what? That the angle gamma this time, the angle gamma is larger than the angle beta. And that means that the cosine of gamma is going to be strictly smaller than the cosine of beta. And what does that mean? Cosine of beta over cosine of gamma. Cosine of beta over cosine of gamma is strictly larger than 1. This factor will be strictly larger than 1. And from our relation, remember, cosine of gamma is strictly smaller than cosine of beta. So if we multiply this through by -1 and add 1 to it, what will happen? It will happen as follows. What will happen is the following: 1 minus cosine of gamma will be strictly larger than 1 minus cosine of beta, because remember, the gamma is larger than beta, cosine of gamma is strictly smaller. Multiply by -1, flip the sign, add 1, there you go. So when we divide this through by 1 minus cosine of beta, strictly larger than 1, a real number strictly larger than 1 times a real number strictly larger than 1. The result is a real number strictly larger than 1. So what is the answer? What is the outcome of this analysis of purely mathematical analysis. The outcome of this purely mathematical analysis is the following. This number over here is strictly larger than 1, and that means that the mathematics has a good dollar on the fact that it takes more work to tip over a uniformly dense cube via one of its vertices. So here we pay attention to vertices. Then it takes to flip a uniformly dense, comparably sized right circular cylinder. You see, in plain English, the work that we need to flip over a cube is strictly larger than the work that is needed to be done physics work by the force of gravity applied to the center of mass, rotating, lifting, yada yada. You guys know the drill. We're going fast and furious over here, and that is the result. This is the mathematics. The physics is more work to tip over a cube via one of its vertices than it is to tip over a comparably sized right circular cylinder. And back into the spoken language, it is easier in this case to tip over a uniformly dense right circular cylinder than it is to flip a uniformly dense cube when the tipping over is done via one of the vertices of a cube. And this is the answer to the second case. And what have we learned in this segment? Well, in this segment we learned three fundamental things. First of all, these two cases when a uniformly dense cube can be tipped over with respect to a fixed edge or a fixed vertex tells us what? That in physics, just like in mathematics, the answer to the question posed is very sensitive to the precise wording of that question. And philosophically, that means that in physics, just like in mathematics, we need to understand what we are saying and say what we mean. Say what you mean, understand what you're saying. That's number one. Number two, we learned about this little wonderful template, heuristic template, or a miniature framework, or a plan of action for answering seemingly vague physics questions and for solving seemingly vague physics problems. First, we need to translate the spoken language notions into the language of physics. Step number two, physics into mathematics. Step number three, solve the underlying mathematics. Step number four, mathematics into physics. Step number five, physics into spoken language notions. That little framework makes it easy and straightforward to do arbitration and refereeing, because the person, the site observer, or a neutral referee who is reading, let's say, your work, can zoom through this template and say, this is where you made a mistake. You can go back, agree or disagree, prove, for example, that you did not make a mistake, or admit, yes, the mistake was right here. We're all humans, we make mistakes. It is easy to diagnose where in this chain of language to physics, physics to math, where did you make a mistake? Keep going and iterate over the process, over all the mistakes, until we're all the physicists in the room agree that there are no mistakes in your reasoning and the conclusion is the correct one. Here we reach the proverbial truth. That's the second thing we learned. And the third thing that we learned, the fundamental one, is that physics essentially boils down to an exact solution of an approximate problem. Now, this is it for the problem, physics problem S2P1, and we will move on to a new challenge next. Starting with the next episode, we will begin a dedicated study of our officially final problem-solving approach called mathematical equivalence. I specifically reserved the study of that problem-solving approach to the very end of our problem-solving curriculum, if you will. And it so happens that we will study that at the very end of the second season on our channel, because that problem-solving approach requires a reasonable amount of both mathematical maturity and power of abstract cognition. And this problem-solving approach also intertwines with the ideas that we covered in this episode in the previous segments when we were solving a physics-related problem. In general, of course, you will not be so formal in your presentation. The reason that I formalize these steps is for demonstration and pedagogical purposes. Once we all understand what these steps are, we will follow them consciously or unconsciously, but there is no need. Relax, have fun. There is no need to list all these steps. We do this, we do that. There is no need for that. As long as you know the program that needs to be done, carry on with the program, and the indoctrinated people will see your work through and they will see, okay, this is what's going on, and we all understand that. Now, as a preparation for the study of the problem-solving approach, to which I refer mathematical equivalence, we will solve the following problem. This will be the problem S2E51. Remember, we're flip-flopping through the letters that designate the problem numbers. M stands for the problem in mathematics, P stands for the problem in physics, and CS stands for the problem in computer science. This, pay attention, we're switching gears fast. S2E52, this is the problem in mathematics, and it is a fairly difficult problem, especially for newcomers, because the problem-solving approach that who study this problem unlocks is fairly difficult too. So this is a sort of three-pronged problem. The idea here is the following. Let's try to solve the problem number 1. In the problem, we're given 2 lab mice, 9 visually indistinguishable bottles of wine. Precisely one of these bottles, one bottle is poisoned, and the objective in this little problem, this is a I don't know, 30 to 45 second problem. Find a testing scheme according to which we can find the single poison bottle in 2 tests or 2 tastings. Now, the definition of a tasting is the following. Mix a cocktail of wines taken from any bottles you wish, put it in a spoon, feed it to one mice, feed it to the other mice. This is one tasting or one test. So cocktailing or mixing wine from different bottles is allowed. So that's the problem number 1. It is a very straightforward kindergarten variety problem. You should be solving this problem even geometrically in about a minute or less. So go through the motions, solve this one. The second problem we already solved, but here for the people, for the viewers who join us mid-season and miss this the way we solve this problem, I will have it in the comments. The episode name, season 2 episode, whatever, the problem number, you guys will be able to find it here. We have 9 visually indistinguishable coins. 1 is fake. Its weight quality is known. It's fake and heavy, or heavy and fake and light. It doesn't matter. Let's say it's fake and heavy. For definitiveness, let's say it's fake and heavy. We're given 1 properly functioning set of pen scales, 2 pen scale, traditional, everything is fine. So here the objective is to find the testing scheme according to which the fake coin can be identified, again, with absolute certainty, no probabilistic arguments, with absolute certainty, no probabilistic arguments. Find the 1 bottle that has poison wine in it out of 9 with absolute certainty. Find the 1 fake and heavy coin out of 9 visually indistinguishable, that is with absolute certainty. That is fake and heavy. 1 out of 9 visually indistinguishable bottles. Now, once you do all this work, this is the meat and potatoes of this problem, and this is where the intellectual effort should be concentrated. Here, answer, try to do your best. If you cannot, write down your ideas and then compare your ideas to mine. Can one solution, if you obtain 2 solutions, can one solution of these problems be automatically or mechanically converted into the solution of the other problem? Here, this squiggly over here, it means mechanical conversion or mechanical transformation. So is it possible to take any one solution of these 2 problems, for example, the solution of the 9 coin problem, and mechanically convert it into a solution of the other problem? Or conversely, maybe you think that you can take the solution from this problem with the 2 lab mice and 9 visually indistinguishable bottles of wine, 1 of which is poisoned, and can you mechanically convert it into a correct solution of this 9-coin problem? Think about it again. Nobody cares about one-word answer. Yes, it can, or no, it cannot. The only thing that we care about is the reasoning behind why the answer that you generated is what you think is. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you guys my solution of the mathematical problem and S2M52.